So I want to find the critical values of f of x equal to x cubed minus 6x squared, which I think we've probably done before. It's one of my kind of go-to examples. But what do I want to say about this? Yeah, so we're going to take the derivative, which is going to be 3x squared minus 12x. And we're going to set that equal to 0. And then we're going to find the critical values. Usually we're going to factor as much as possible. So I'm going to factor out 3x. I'm left with an x minus 4. Set that equal to 0. So then I end up getting that x equal to 0 is a critical value, and x equal to 4 is a critical value. All right. So let's go ahead and look. Let's talk about the relative extrema, and also where the function's increasing, decreasing. But those two things go together. So if I look at the first derivative, I should say the number line for the first derivative, and put these two critical values on my number line. And then I'm going to check and see where is my derivative positive, where is my derivative negative. So picking a value larger than 4, like 5, 3 times 5 is positive, 5 minus 4 is positive, the whole thing is positive. And then between 0 and 4, I can pick 2. 3 times 2 is positive, 2 minus 4 is negative, product is negative. And then over here, less than 0, I can pick something like negative 1. And come on, admit, okay. 3 times negative 1 is negative, negative 1 minus 4 is negative, but negative is negative is positive. I will also point out, fully factoring whatever your derivative is makes it easier to both find the places where it's equal to 0 or undefined, and also it makes it easier to test points that are not those, right? You have to test points that are in the interval, not the critical values. And if you fully factored it, it's easier to determine if the product is positive or negative when you plug in a point. So it's really, really in your interest to fully factor your derivative if you can. So then we know that the function itself is increasing, decreasing, increasing. And we know that we have a relative maximum at x equal to 0, because the function is increasing and decreasing. We have a relative minimum at x equal to 4. Okay. There's like a few different directions I feel like we could go here. Let's go in this direction first. So what I actually want to ask now is, now we'll go this way. What about, I want to know, what are the absolute extrema of the same function, f of x equal to the same thing, x cubed minus 6x squared. And typically, although technically not always, but almost always, when we ask a question about what the absolute extrema are, we have to give an interval. Usually a closed interval. Typically, although there's a homework problem that actually defies this, but typically when you're asked about absolute extrema on a closed interval, that function needs to be continuous on that interval. It doesn't mean a function couldn't have absolute extrema if it was discontinuous, and we're going to see an example. But the idea here is that usually we need it to be continuous so that we don't have weird things. I should say, to guarantee that there is both an absolute minimum and an absolute maximum, the function does have to be continuous. If it's discontinuous, you might still have one or the other, or even both, but you're not guaranteed to have them. So this is an example of a function where you're definitely guaranteed to have absolute extrema. Here's how you find them. So again, I'm going to look at the information I have from the first derivative. I know that my critical values were x equal to 0 and x equal to 4. Right, from the other work we just did, right? And we even know, right, we could even draw the first derivative number line if we really wanted to. So we can say, hey, look, I know that my function, here's 0, here's 4. I know the derivative is still positive, negative, positive. So my function is increasing, decreasing, increasing. But then I'm going to stop, right? I'm going to I'm going to start at -1, I should say, right? Start. And I'm going to end at 7. The idea here is that at -1, whatever the value is, the function is going to be increasing until I get to 0, and then decreasing until I get to 4, and then increasing until I get to 7. I don't know if I've drawn this right. I think I have, but the point is, right, here are the candidates for the extreme values. I have -1 comma something. We know 0 comma 0, right? Because if you plug in 0 to the function, you get 0. I have 4 comma something, and I have 7 comma something. So here's the idea with absolute extrema, meaning the thing that is bigger than everything else is the absolute maximum, the thing that is smaller than everything else is the absolute minimum. So if you have a function that's continuous on a closed interval, the absolute extrema have to occur either at the critical values or at the endpoints. So if I want to find the absolute maximum, what am I going to do? Well, I'm just going to see where the function is the biggest. So I'm going to look at f of -1 and f of 0 and f of 4 and f of 7. Right? It couldn't be anywhere else. It couldn't be at like at 2, for example, because we know that at 2 the function is decreasing. So on the right, because the derivative is negative at 2, so on the left side of 2 the function is bigger, on the right side of 2 the function is smaller. So 2 couldn't be a maximum and it couldn't be a minimum. That's why we have to say that, oh, the critical values, the absolute extreme values can only occur at critical values or at the endpoint, right? Because the endpoint, right, the function is increasing, but since it's increasing on the left and we're not looking at the right side, this is kind of a possibility for, oh, maybe that's the biggest thing. It's definitely bigger than everything that's next to it because we're not including the right side of it. So endpoints or critical values are the only candidates for absolute extrema. So the nice part about this is it's actually fairly straightforward to test. You find the critical values, you find the endpoints, which are given, and then you just plug them all into the original function. This is, again, a place where you're going to see that it's going to be to your benefit to factor this as x squared times x minus 6, right? I don't really want to do 7 cubed minus 6 times 7 squared, but 7 squared times 7 minus 6 is super straightforward. So really, if you can, factor a thing. So f of 7 is going to be 7 squared times 7 minus 6, which is 49 times 1. And f of 4 is going to be 4 squared times 4 minus 6, which is 16 times -2, which is -32. F of 0 is 0. And f of -1 is -1 squared, which is 1 times -1 minus 6. So 1 times -7. Great. Which of these 4 numbers is the biggest? -7, 0, -32, or 49? Clearly it's 49. So we have an absolute maximum at x equal to 7. The absolute maximum value is the function equal to 49. So the absolute maximum is at x equal to 7 with a value of 49. The absolute minimum is, well, what's the smallest thing? That's -32. So the absolute minimum, I should say, we usually say where it's at before what it is. So the absolute minimum is at x equal to 4 with a value of -32. So that's typically our process for finding absolute extrema. We find all the critical points in the interval, and then we ask ourselves, okay, where is it biggest, where is it smallest? Let's look at 2 more examples. Yeah. I've got one more example I want to show you just because there's something that often comes up. I want to do that one, sure. We can, yeah, why not? That's why not. Sorry, I'm trying to make up one that's like not super lame, but also interesting. Sorry, one moment while my brain figures out what I'm looking for. Fine, let's just do this. Let's do f of x equal to, sorry, 1 second. Let me just call something real quick here. Yeah, I want that. I want this times this. Sure, fine. Doesn't matter. Sorry, one moment while I figure this stuff out. Sure. Sure. So I want x cubed plus 2x squared minus 4x plus 1. And I want that to be on the interval from, sure, let's do -3. Yeah, sure. Let's do -5. -5 to 2. That's a 0. Okay. So again, we want to find the absolute max ending of f of x equal to x cubed plus 2x squared minus 4x plus 1 on the interval from -5 to 0. Same process. We're going to find the critical values. So we're going to, let's see, the derivative here is going to be 3x squared plus 4x minus 4. And we're going to set that equal to 0. This should factor, because I just literally designed it to factor. But the thing is, how do you factor this? So there's a couple ways to go about factoring a quadratic if you've got a coefficient that's not 1. So I know it's going to be 3x and then x. And I need things that multiply to -4, and then when I multiply it out, add it to positive 4x. There's a couple different ways of doing this. I feel like the way that is the most consistent is you do 3 times -4 is equal to -12. And then you need numbers that multiply to -12 and add it to positive 4. The numbers that do that are positive 6 and -2. Now here's the place where people usually go wrong. They usually do something like, say, it's x minus 6 times x plus 2. That's not it. What we have to do is we have to rewrite the 4x as 6x minus 2x. So this becomes 3x squared plus 6x minus 2x minus 4. Right? The 4x is the 6x minus 2x. And then the idea is that if this works out, right, like if we found two numbers that multiplied to a times c and added up to b, then if we write it this way, we should be able to factor by grouping. From this first part, I can factor out a 3x. I'm left with an x plus 2. From this second part, I can factor out a -2. I'm left with an x plus 2. And these two pieces have to end up being the same, otherwise it doesn't work. You can factor out an x plus 2 from both of those. And we're left with a 3x here and a -2 there. So we factored it, and our critical values are x equal to -2 and x equal to positive 2/3. Great. We have our critical values. We have our endpoints. Let's plug them into the original function and find out what's the biggest and what's the smallest. Okay. So here's the deal. We're definitely going to do f of -5. Okay, fine. Let's just calculate it real quick. F of -5 is -5 cubed is -125. 2 times -5 squared is 2 times 25, which is 50. -4 times -5 is 20 plus 1. That's -75. Plus 20 is -55, plus 1 is -54. Sorry, okay. Let's see, f of 0 is much more easy to calculate. F of 0 is 0 plus 0 plus 0 plus 1. Be careful, right? Make sure you're plugging things into the original function. We got f of -5, we got f of 0, we need f of -2, which is going to be let's see, -2 cubed is -8. 2 times -2 squared is +8. -4 times -2 is +8. And +1. So these -8 cancel, 8 plus 1, which is 9. And now here's the deal. We don't plug in 2/3. Why don't we plug in 2/3? Because 2/3 is not in the interval, right? 2/3 isn't between -5 and 0. So we can't really consider it being a place where you could have a max or a min, because we want to know what is the absolute maximum or minimum of this function where x is between -5 and 0. This critical point here doesn't count. So we can see that the absolute minimum is right there, and the absolute maximum is right there. So the absolute max, sorry. Trying to do a minimum and a maximum at the same time. So the function has a minimum at -5, -54, has a maximum -2, 9. If you're interested, I can show you what the graph of this looks like. Let me see, do I want to erase stuff? I think, yeah, let me just do this. We'll leave this up. So this did factor as 3x minus 2 times x plus 2. And if you wanted to, you could look at the number line, just kind of see the graph. So looking at the number line, we can see that I'm doing the whole number line. My critical point's -2 and +2/3. And it's definitely positive over here and then negative and positive. So it's increasing, decreasing, increasing. So I can see that, so -2/9, so it's like increasing until you get to -2/9, and then decreasing until you get to 2/3, comma, whatever that would be. We know that f of 0 is 1, so it's like this, and then something like this, and there's your 2/3, and then be increasing afterwards. So this is the whole function. Oh, sorry, someone's trying to come in. But if we are just looking between -5, which is way over here. So here's the point, -5, -54, and here's the point 0, 1, and here's the point -2, 9. And if you're just restricted to that part there, well, clearly this is the most negative thing, or the absolute minimum, and this is the absolute maximum. Anything else I want to say about this? Right, but this relative minimum here gets left out because it's not in the interval. One more of these, and then we'll do something different. This last one, when I first read it, I was like, that can't be right. That seems totally wrong, but it is totally right. It's kind of weird. Well, it's weird to me because usually these questions are on for a function that's continuous on the interval. I will point out that the question that I'm about to talk about does say if there isn't an absolute maximum, you're supposed to write something like none. So, and this problem definitely won't have either an absolute max or an absolute min. So let's look at this problem. It's f of x equal to, I have a 5, but someone sent me a 3. It doesn't really matter. 3 times 1 plus 1 over x plus 1 over x squared. And we're on the interval from, what have we got here? -6 to 2. Notably, this function is undefined at 0. So we definitely can't have anything there, right? There can't be an absolute max or an absolute minimum there. It's undefined there. But we still need to find all the critical values. So I'm going to take my derivative, which is going to be kind of a pain. If I'm taking the derivative of this, I might rewrite this as 3 times 1 plus x to the -1st plus x to the -2nd, just to make it a little bit easier to differentiate. My derivative is going to be the constant multiple hangs out. Derivative of 1 is 0. Derivative of x to the -1st is -x to the -2nd. And the derivative of x to the -2nd is -2x to the -3rd. Okay, that is not super helpful written that way. So let's do a little bit of simplifying. That's going to be 3 times 0 goes away, negative 1 over x squared minus 2 over x cubed. And I'm going to multiply the negative 1 over x squared by x over x, taking the common denominator. So I'm going to have 3 times, I might as well, no, let's see what's right. Negative x over x cubed minus 2 over x cubed. If I factor out a negative 1, this is going to be negative 3 times positive x plus 2 over x cubed. So it looks like my only real critical value is x equal to negative 2. Although I'm also going to include the pseudo-critical value, x equal to 0. And I think for this one, yeah, we really do need to kind of, yeah, well, let's do the usual process and then talk about what we might be missing here. So I'm going to do my usual process. I'm going to evaluate the function at the endpoints and at the critical values, the real critical values. Right? So I can't plug in 0. It's not an actual critical value. If you plug in 0, it'll be undefined. So what I'm going to do is I'm going to say, okay, what's f of negative 6, f of 2, and f of negative 2. And those are the 3 things, right? These are my endpoints, and that's my critical value. And this one, again, not really a critical value. So if I plug those in, let's see what happens. And the numbers are not going to be nice here. F of negative 6 is going to be 3 times 1 plus or minus 1 over 6 plus 1 over 36. That's not nice. So you know what might be a good idea before I actually do this would be to maybe simplify this expression just a little bit to make it a little bit easier to see what's going to be the biggest. So I might multiply this by x squared over x squared and this by x over x to write this as 3 times x squared over x squared plus x over x squared plus 1 over x squared. That might be a little bit nicer to plug in negative 6 and 2 and negative 2 and 2. So let's see. F of negative 6 is going to be 3 times 36 minus 6 plus 1 all over 36. So that's going to be 3 times, let's see, 36 minus 30, 31 over 36. I can cancel a 3 and get 31 over 12. Okay, that's a number I can at least kind of make sense of. F of 2 is going to be 4 plus 2 plus 1, I should say 3 times 4 plus 2 plus 1 over 4. That's going to be 21 over 4, which I can multiply by 3 over 3 to get 63 over 12. The reason I would do that is to be able to compare these and be like, oh yeah, that one's bigger. And then finally, f of negative 2, it's going to be very similar to this one. It's going to be 3 times 4 minus 2 plus 1. So that's going to be 3 over 4. So that's going to be 9/4, which is times 3 over 3 is 27 over 12. Okay. So here's the issue. If we were not being careful, we would say there's your absolute maximum at 2. There's your absolute minimum at negative 2. The problem is one of those is not right. Let's see why. So what I'm going to do, so I don't want to graph this, not because we shouldn't graph it, because it might be kind of, it's hard to graph this without like actually doing all the stuff. And we're not trying to do all the stuff. We're just trying to figure out, do I have an absolute max or an absolute min? So instead of graphing it, what I'm going to do is I'm going to look at the number line. Yeah, the number line for the first derivative. So essentially I'm doing the first derivative test, but not really. Yeah, okay, let's look at this. So there's my first derivative. And again, we're really only concerned with what's happening between negative 6, that's kind of our endpoint, and positive 2. Between negative 6 and 2, you've got the critical value of negative 2 and the pseudo-critical value of 0. So if I pick a number larger than 0, but still smaller than 2, like 1. If I pick 1, my derivative is going to be positive over a positive times a negative, so it's going to be negative overall. be something between -2 and 0, like -1. It's going to be positive on top, negative on the bottom, negative over here. So negative times a positive divided by negative is going to be positive. Over here between -6 and -2, like -4, it's going to be negative on top, negative on the bottom, negative over here. So negative, negative, negative is negative. So here's what we've got. The function is decreasing, then increasing, then decreasing. So the problem here is that even though this number here is the biggest number, so right, so the picture kind of looks like this, right? Watch, I should say. So that's our absolute maximum. But the problem is the function is decreasing to get to that point. That doesn't make sense that that's the absolute maximum. Here's what's going on with the picture. What's going on is at -6, we know the function's equal to this value. So if I started graphing it, right, over here at -6, the function is positive 31/12, so it's something like this. And then as we go to -2, f of -2 is 27/12, so it gets a little bit smaller, not a lot, right? It kind of just goes down a little bit. And then after -2, it increases to infinity. So we have a vertical asymptote there. And then on the other side of 0, it decreases until we get to 2, which has a value of 27/12. So yeah, of the 3 points we checked, that one is definitely the biggest. But look, there's all this other stuff that's infinitely big. So this particular function, this example, has an absolute minimum at -2, because we can see that that point there is the smallest of all the things on the graph. It also has the smallest value, right? So it's smaller than everything else, and also the function is decreasing to the left of it and increasing to the right, which means it is a minimum. On the other hand, this endpoint 2, although it is the biggest of the values we checked, it's definitely not the biggest the function is, right? The function is decreasing to get to that point. That point can't be the biggest. It's actually kind of one of the smallest ones. So when you have a function that is discontinuous, finding absolute extrema is a little bit more of a challenge. You have to be a little more cautious about what things look like. I would say if I had to do this problem, what I actually did when I was doing this problem, I was like, that seems weird. I just threw the graph on Desmos and was like, oh, I can look at the points -6, -2, and 2, and I can totally see that one of those is the smallest, and then there's no absolute maximum. Okay. Let me take this up. Oh, can we grab my, off my water out there? I'll be right back. Sorry about that. Okay, I think we'll circle back around to talking about more graphing stuff. But I feel like a number of people had quite a few questions about related rates. So I feel like we should spend some time on that. So let me hold these up here. One sec. No, you're not related to rates. You're also not related to rates. I've got more first derivative, second derivative stuff. Sure. There we go. You're kind of related rates. We can do that. So I've got 2 related rates questions I want to do. Let's do the seemingly, let's say this one isn't so much a related rates question, it's just kind of a use derivatives to find the thing. So this is less of a related rates problem, but somebody asked it, so we'll do it anyway. And then we'll do this plane problem that a couple people asked about. It seems challenging. Let's look at this one. So this one is just asking, find the rate of change of x with respect to p for, I see that. Okay, this is an interesting question. For p equal to the square root of 700 minus x divided by 4x. So they're asking us to find dx dp. But the problem is, typically to find dx dp, you were having to solve for x as a function of p, right? We would love to write that x is a function of p, and then dx dp is equal to f prime of p. Now I only have a screenshot of this problem, so I'm not. Let me look at one thing here. Let me see if I can. Nope, I don't see it. All right. Yeah. I'm just curious if this problem is showing up in the homework. I just want to see because there's two different ways we can do this problem. And I don't know if there's a specific way that it is meant to be done. So let me take a look. Do I see the problem there? I do not. I do not. Okay. And then let's see if I can see it here. Sorry, I just want to see if I can actually see the problem or if I don't. I don't think I'm going to do that. Yeah, that's fine. Okay, let me just talk about, I'll do it both ways. So I imagine if I had to guess, again, I am guessing here. I think the way that you're intended to do this problem is to not solve for x, is to use implicit. So there's two ways we can do this. We have to be careful here to make sure our frame of reference is correct. So the idea here is that p is the independent variable and that x is the dependent variable. So it is true that we could write x as a function of p. So if I'm going to take the derivative, what I'm going to try and do, I'm going to try and do implicit. So the problem here is that p is like our x and x is like our y. Right? Y is the function of x is the function of p. So if I was going to differentiate both sides of this, I would get, and I feel like the more I look at this, the more that seems like it's going to be the wrong way to go. Like we could do that. I don't know. Let me go the other way. Let's do it the way that might be better. I don't know. Let's solve for x. So square both sides. P squared equals 700 minus x over 4x. Multiply both sides by 4x. So 4x p squared equals 700 minus x. Group your x's on one side so that 4x p squared plus x equals 700. Factor out your x. X times 4p squared plus 1 equals 700. And then x is equal to 700 divided by 4p squared plus 1. And then we can find dx dp. So dx dp, using the quotient rule, I'm going to kind of, so pay attention because I'm going to kind of, I'm not going to skip steps, but I'm not going to write down everything here. Dx dp is the bottom times the derivative of the top, which is 0. So you're just going to get a 0 minus the top times the derivative of the bottom, which is 8p divided by the bottom squared. 700 times 8 is 5,600. So this is negative 5,600p over 4p squared plus 1 quantity squared. That is probably what they want you to do. If someone wants to chime in about this one, I'm happy to hear what you have to say. The other way you could try doing this one seems a little crazy. You could, if you really wanted to, say that this function is, 700 minus x over 4x to the 1/2 power, and then you could differentiate both sides implicitly. So you could say, okay, what's the derivative of p? Well, the derivative of p is 1 because we're differentiating with respect to p. And what's the derivative of this side? Well, there's some stuff to the 1/2 power is 1/2 times your stuff. The negative 1/2 power times the derivative of your stuff. Yeesh. Oh, I'm regretting this already. Bottom, derivative of the top, minus the top, times the derivative of the bottom. Oh God, over the bottom squared. All times the derivative of x. sorry, this is terrible. So looking at that, it seems like a really bad idea to do it that way. So I agree to the person who wrote me the private comment. This does not look very friendly. So I would have to guess that they do not mean for us to do it this way. If it's doable this way, it's gross. So I'm going to leave it at having done it this way and say that's probably what we should do. So this does lead me to this one, say like, if they're asking you to differentiate something, so like for example, I'm gonna try and write it in variables that might seem a little bit more easy. Right? If I said something similar but not exactly the same, like if I said x is equal to the cube root of, I don't know, 600 minus y over 7y, and I said find dy dx, it's probably going to be in our benefit to solve for y if we can. And this one and the previous one, it definitely was possible to solve for our dependent variable, our function. So yeah. Again, I'm not 100% sure that's what they wanted, but I'm pretty sure that's what they wanted. All right, so that was not a related rates problem, but it did have a rate of change. Yeah, so let's look at this other air traffic controller problem. A couple different people sent me this problem with a couple different numbers. So sorry if I'm not using your numbers. I can just make up totally different numbers. But my hope is that whichever numbers they gave you are going to work out decently. So let's take a look. So here is the setup. And I'm going to read the problem and I'm going to draw a picture. An air traffic controller spots two airplanes at the same altitude converging to a point as they fly at right angles to each other. Okay, so here's what so to kind of interpret that, I'm thinking here's the point they're flying to, that they're going to crash at if I don't do anything. So there's one plane here flying that way, the plane A maybe, and there's another plane here flying that way. Okay, and they're flying at right angles to each other. One airplane is 120 miles from the point and has a speed of 240 miles per hour. So let's say that sure. Let's say it's this one because this one looks slightly closer. So this distance, well, I'm not going to say that distance is 120 miles, even though the point of interest is 120 miles. That distance is changing. I'm going to call it y. And similarly, this distance is also changing. I'm going to call it x. Yeah, that's interesting. Okay, so let's check this out. So this plane here is flying at, oh, sorry, I said this plane. This plane is flying at 240 miles per hour. This is at 240 miles per hour, and it's 120 miles away. And this plane is going at 320 miles per hour, and it is 160 miles away. So clearly, if we don't do anything, they're going to crash in 30 minutes. Right? I don't think you don't need to know anything else about them to know that, like, in 30 minutes, if I'm going 320 miles an hour, in half an hour, I'm going to travel half that distance, which is 160 miles, and I'm going to hit the point. So, yeah, I feel like the second question should be the first question here, because you don't really need to know how fast the distance between the planes is changing to know anything about that. Although I guess I think you can draw this picture, but okay, I know they're going to crash in 30 minutes. So I need to set up the whole kind of system. So I know this is the distance. I'm going to say the planes are here and here, just to kind of make it easier. So let's call this distance S. I know how x and y are changing. I know that dx, dt, well, I'm going to say something in a minute. And I know dy dt is. Now here's the thing. Because of the way this picture is working, let me ask you guys. As my plane moves closer to the point, is x increasing or decreasing? As this plane gets closer, yeah, it's decreasing, which means dx dt should be negative 320. I don't know if it's actually going to matter, but it probably is going to matter. In a similar way, y is also decreasing, right? Y is the distance between your plane and the eventual point of collision. That distance should be getting smaller if they're going to collide. So dy dt should be negative 240 miles per hour. And then we want to know, what is ds dt at the moment of interest, right? How fast is the distance between the two planes changing? So first of all, it should be true that ds dt is negative because the distance should be getting smaller and smaller and smaller. Typically, the way I would probably answer this question, yeah, so in fact, so the way it's worded is, at what rate is the distance between the planes changing? So your answer should be a negative rate for sure. Let's find that though. So, oh, sorry, calf pain. I need to roll my calf a little bit. Calf is super tight. Sorry. Okay, enough of that. So let's see. Someone asked me a really good question in the reflection, which is, how do we know like the equation when you're dealing with related rates if they don't give it to you? And typically the equation is, I think we talked about this a couple weeks ago, is that it's typically some geometry formula, right? So it really, really matters that we draw the picture correctly so that we can kind of have an idea. Like here, we have a right triangle, so we're probably going to use the Pythagorean theorem. You might also use similar triangles, right? That also come with right triangles, but it's usually one of those two things. Importantly, your equation should relate the variables that are changing, meaning if you know that x and y and s are changing, and you know how these two are changing, and you want to know how this one is changing, your equation should probably have all three of those variables in it. Ours does. Like the Pythagorean theorem is that x squared plus y squared equals s squared. We can't plug anything in until after we have differentiated both sides with respect to time. To differentiate everything, you're going to get 2x times dx dt plus 2y times dy dt equal to 2s times ds dt. Now, if you wanted to, you could cancel all the 2's. Right? You can divide both sides by 2. Great. We divided both sides by 2. Right? Okay. Now we have to plug in what we know and solve for what we don't. We should be able to solve for this, meaning we should be able to plug in for x, dx dt, y, dy dt, and for s. We know everything on the left, right? We know that we're talking about when we are 160 miles away. So at the moment of interest, this distance is 160. This distance is 120. So I know that x is going to be 160 miles. Dx dt is 320 miles per hour. Y is 200. Oh, sorry. So it's not positive 320 though. It's negative 320, right? And then y is 120 miles, and dy dt is negative 240 miles per hour. Now, what is s? So we could use the Pythagorean theorem to figure out that, s squared equals 160 squared plus 120 squared. I don't want to do that, and I'm pretty sure I don't have to, because I can see that 120 is really 3 times 40. 160 is 4 times 40. And look, I have a 3, 4, 5 right triangle Pythagorean triple. 9 times out of 10, if you're dealing with a right triangle with a Pythagorean theorem, it's going to be something like a 3, 4, 5, or a 6, 8, 10, or a 5, 12, 13, where the sides are nice integer values. So if you see two sides, you're like, that's probably a 3, 4, 5 triangle. They're just all the sides are multiplied by 40. It is, right? This is 3 times 40, this is 4 times 40, the hypotenuse is 5 times 40. So my S value there is 200 miles times ds dt. And then to find the answer, we have to multiply that. So I might, no, I don't know. Like, I don't want to do the take here, but I guess I will. So let's divide everything by 200. So actually that's going to work out okay. So if you divide this by 200, I'm going to divide this by 10 and this by 20 to get 16 times negative 16. I'm going to divide this by 200. I'm going to get 12 times negative 12 equals ds dt. Right? So I divided this by 200, dividing by 10, dividing by 10, and dividing by 2. Dividing by 10, dividing by 10, dividing by 2. That's 200. So then 16 squared is 256. 12 squared is 144. Ds dt. So that's going to be 400, negative 400 miles per hour. Cool. So these planes are, the distance between the planes is changing at negative 400 miles per hour, or a more normal, non-mathematical way of saying this would be that the distance between the planes is decreasing at 400 miles per hour. You wouldn't say negative, but to answer the question the way it's phrased, you do need to have the negative in there. The second question, how much time do you have until the airplanes collide? You could just not have done any of this and say, well, I know it takes 30 minutes for this plane to get here and 30 minutes for that plane to get there. Or you could say, well, I know the planes are 200 miles apart and their distance is changing at negative 400 miles per hour. So in a half hour, you'll have gone 200 miles, meaning the distance between them will have decreased by 200 miles and they'll crash. Of course, we're not going to let them crash, right? Okay, so yeah, that's a good problem. It's definitely a problem that requires a good job of doing the setup. Right? The actual math, the calculus, is not that hard. Taking this derivative, not that hard. Plugging in these numbers, okay, a little hard, but not that terrible. But it's really kind of making sure the setup is right, making sure especially that you realize that your rates of change, I erased the other one, sorry, that your rates of change are both negative. Right? That's kind of a key thing. So you really have to pay attention with your picture. Right? If your picture of something's getting smaller, its rate of change should be negative. Okay. Yeah, good question. I like that one. All right, let's go back. Certainly, if you guys have more related race questions, we can answer them. But I feel like people had a lot of questions about, something in my eye. About finding relative extrema, absolute extrema, which we already kind of did. And then just talking about first and second derivative test, all that kind of jazz. So let's do something. We found the derivative. Why do you not have 2x and 2y in the equation? Well, we did. Oh, sorry, Marshall. We did, but remember I canceled all the 2's. So I had 2x times dx dt plus 2y times dy dt equal to 2s times ds dt. And I said, let's just divide everything by 2. That almost always happens when you have a Pythagorean theorem equation like this. You're always going to get 2 whatever times d whatever dt plus 2 whatever times d whatever dt equal to 2 whatever times d whatever dt. And you can always just divide those sides by 2. All right, let's look at this one. This one's so let's look at this one. So this is section 3.1, part 1, problem 6. Let f of x equal 5x times the cube root of x minus 8. And we want to find the critical values. So they ask what values is the derivative 0 or undefined, which means find the critical values. And whenever I'm finding the critical values or differentiating the function with a root, I always want to rewrite the function as, instead of a root, a fractional power. So 5x times x minus 8 to the 1/3 power. So let's go ahead and take the derivative. We are going to have to use the product rule. So the derivative of 5, so I'm thinking of this part times this part. So the derivative of 5x is 5 times x minus 8 to the 1/3 power plus 5x times the derivative of x minus 8 to the 1/3 is going to be a 1/3 times x minus 8 to the negative 2/3 power times the derivative of the inside, but the derivative of x minus 8 is just 1. But it's still good to think about the chain rule if your stuff to a power is anything more complicated than just x. Okay. For problems like this, especially when you're using the product rule, you're almost always going to have to factor. So what can I factor out? Let's see, I can definitely factor out a 5. And I can definitely factor out an x minus 8 to the smaller power. Right? If you're factoring x cubed plus x to the 7th, you're factoring out an x cubed because it's the smaller power. And it's x cubed times 1 plus x to the 4th. Or if you were factoring x to the negative 3rd plus x squared, you're going to factor out the x to the negative 3rd because the negative 3, it's negative. It's definitely smaller than positive anything. So here you factor out an x to the negative 3rd, and you'd be left with 1 plus, let's see, 2 minus minus 3 is 5. So when you factor out a negative power, the remaining power actually gets larger because you're subtracting out a negative thing. So here I'm going to factor out an x minus 8 to the negative 2/3 because that's the smaller power of x minus 8. From this part, I'm left with, well, I don't have a 5 because I factored out the 5. I factor out an x minus 8 to the negative 2/3. So x minus 8 to the 1/3 divided by x minus 8 to the negative 2/3 is x minus 8 to the 1/3 power minus negative 2/3, which is just x minus 8 to the 1. It's almost always whatever you have to the 1. If you're not sure, you can always do a quick mental check, but if you multiply this back through, multiplying this by this, you add the powers, and negative 2/3 plus 1 is negative 2/3 plus 3/3, which is positive 1/3. So it does get you back to where you just were. Plus, from this part, I factored out a 5. I didn't factor out an x. I'm left with an x. I also am left with a 1/3. And then I factored out the x minus 8 to the negative 2/3. So that's gone. Now, another thing we can do. So here's, yeah, I don't know. I'm kind of torn. I don't love this personally. So here's what we've got. We've got 5 times x minus 8 to the negative 2/3 times x minus 8 plus 1/3 x. X plus 1/3 x is 4/3 x. So you can say we have 4/3 x minus 8. That's not the best. I should actually get a common denominator here and say this is 5 times x minus 8 to the negative 2/3. 4/3 x minus 8 is 4x over 3 minus 24 over 3. So then I can combine that as 4x minus 24 over 3, and I can factor out a 4. So in the end, sure, I can say that my derivative is going to be, I'm going to rewrite this part as 5 over x minus 8 to the positive 2/3. I think positive powers are usually the way to go when you're finding critical values. And then I'm going to have over here, I said I could factor out a 4 from the top. So I'm going to have 4 times x minus 6 all over 3. Okay. Any questions before we start talking about the critical values? Because I'm going to erase this so that actually, I guess I can just go to the other side of the board. How about, I'll do that in case we need to come back to this. I'll go there. So, by the way, I got a new eraser. I'm really digging it. You know, it's the highlight of my week. New eraser. Not getting terrible black dust everywhere like my old eraser was. So let's see. Derivative. That. So my derivative here is 5 over x minus 8 to the 2/3 power times 4 times x minus 6 over 3. Yeah, cool. So we want to see what makes this 0 and what makes this undefined. So what makes this undefined, everybody? X equal to what? Yes, it's my favorite number. Guys like, oh, he wants us to do a thing. Yeah. Thanks. Thanks, one person. X equals 8 makes it undefined. If you plug in 8, you get 8 minus 8 in the denominator. So 0 in the denominator, which means undefined. What makes it equal to 0? Well, not 8. But if you plug in 6 for x, you get 6 minus 6 in the numerator, which is 0, and 0 times anything is 0. I do want to strongly emphasize here. X equal to 8 is a real critical value. It's not one of those fake pseudo-critical values that I've talked about. It's a real one because 8 is in the domain of the original function. In fact, the original function is defined everywhere, right? You can plug in 8, you can plug in 6, you can plug in a billion, you can plug in negative 1,000. Cube root is defined for all values of x. 5x also multiplying the other. So this function has domain everything. It's defined and continuous everywhere. All right, so we want to determine, so we found the two values. Now we want to know where it's increasing, where it's decreasing, and I'm also going to talk about everything else. So the thing is, the person who asked me this question, I think well, no, actually, yeah, that's a good question. Well, I don't know. They wrote their answer. I don't know if they were asking me this question because their answer wasn't right or not. But let's take a look at the number line. So I got 6. I got, right, the only numbers that go on the number line for the first derivative are the critical values and the pseudo-critical values that there aren't any here. Okay, so pick a number bigger than 8. 20. 4 times 20 minus 6, positive. 20 minus 8, positive. Positive, 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 positive. The whole thing is positive. So the function's increasing. Between 6 and 8, we're going to pick 7. 7 minus 6, positive. 7 minus 8 is negative, but a negative thing to an even power, even if it's an even power divided by an odd power, right? If your fractional power has an even numerator, it's going to end up making it positive. Right? -1 squared is 1, and the cube root of 1 is still 1. So it's still positive, which means it's increasing there. And then f prime of, sorry, brain. If we pick something less than 6, like 0, plug in 0 here is positive, plug in 0 here it's negative, so the whole thing's negative. So, reading the question, what intervals is the function increasing, or sorry, decreasing? Let's talk about decreasing first. So decreasing is definitely decreasing from -infinity to 6. Increasing. So whoever asked me this question, I think, oh, so if you were getting that your answer was wrong, and I don't remember who asked me this question, but I can see that for your answer does have endpoints included. So typically, unless the book specifically says to, or your teacher specifically says to, when you're talking about where a function is decreasing or increasing, it is usually an open interval. But for some reason, your book or your teacher might have specified that it should actually include the endpoint. There are good reasons for doing it either way. Most textbooks, teachers, people default to doing it this way, but it's technically not incorrect to do it this way. So if you're encountering trouble with a decreasing or an increasing interval, you should probably default to thinking of it this way. But if that's not working, you can also try this. Increasing, so here's the question. Is it this? Assuming we're not including endpoints, is it this where you don't include the 8, or is it this where you do include the 8? Well, I'm pretty sure it's that, because it's increasing to the left, it's increasing to the right, and it's defined at 8. Right? The function is not undefined there. If you plug in 8, you get 40 times 0, which is 0. The function definitely defined at 8. So I believe our answer should be that it's decreasing on the open interval from -infinity to 6, and it's increasing on the open interval from 6 to 8. If I wasn't sure about that, I would graph it. So let's take a look at the graph. Wow, the time has gone by. Okay. Yeah, that's a pain. Someone just said to me that the WebWorks problems come from multiple textbooks, which is why different questions have different very particular answer codes. So yeah, so the thing I will say about these increasing, decreasing intervals is your answer might include the endpoint with a bracket, or it might exclude the endpoint with a parentheses. I would generally encourage you to default to not including the endpoint and using a parentheses, but if that's not working, then try with a bracket. Sorry, I think what is going on? I'm sorry. I'm looking at the screen. I'm trying to like click on this dumb. I'm like, how can I open a new page? Because I've opened someone's screenshot that has all these tabs open. I think I have an actual, I think my brain is like not working. Like, why can't they do anything with this problem? It's because it's not actually a web browser. That's the problem. You can't open a web browser in someone's screenshot. Did you know that? I'm sure you all knew that. Okay, sorry, let's open Desmos here. Just take a look. Share my screen. Share it up. So here's the problem. 5x times x minus 8 to the positive 1/3. So yeah, 5x minus x minus 8 to the 1/3 power. That looks wonky. So let's first of all, I feel like there should be a y equals, even though it doesn't really change anything. Let's zoom out a bit. So it definitely looks like, looks kind of wild. There's 6, there's 8. So here's what's happening with this function. So clearly, right, decreasing, increasing, and even at 8, why are you being so funky around 8? So right, when you get the problem, the question I guess I'm trying to ask is, why is the derivative undefined at 8? Well, because if you look at 8, this function has a vertical tangent. So if you actually graph x equal to 8, and let's zoom it in a little bit. So, right, I mean, you can't even really see the difference between them. But like, if you look, right, so there's the red graph, and here's this blue line that is the vertical tangent at that point. I wonder if I can do a thing. Let's see. Yeah, that's cool. So there's not quite taking up so much of the graph anymore, but you can see, oh yeah, look, there is a tangent segment at the point 8, 0, and it is a vertical tangent. So the function is still totally defined there. It's totally increasing there, but the derivative does not exist there because the tangent line is vertical, and vertical lines have an undefined slope. But definitely looking at this, it certainly is increasing from from positive 6 forever and ever and ever after that. And as we go further out, you can see that the tangents, become less steep as you move further to the right. Okay. Yeah. Now, I was going to say, should we look at this one for? We should look at this one for more. But that one's kind of gross. So let's look at this other problem someone sent me, which I think will offer some interesting perspective here. Yeah. Let me grab a different example. I've got examples that I know of. So I want to make sure I'm getting to everything. I feel like we've got 13 minutes left. I feel like I should try and hit some. I don't know. People asked about all sorts of things. Sorry, I forgot that I wrote down. I was looking at the screenshot people sent me, but I forgot about the problems I wrote down on paper. So, when it comes to finding relative maxima and minima, I would encourage everyone to use the first derivative test, meaning what we've been doing, where you see if it's increasing, decreasing, or decreasing, increasing to see if you have a maximum. But there is another way you can do things. So let's say we have this function. Let's look at f of x equal to 2x plus 2 over x. And I want to find, again, relative extrema. Also, maybe I want to find concavity inflection as well, which I know we haven't talked about, but try to talk about. And guess we'll have to say more on Thursday. So let's find critical points, critical values. So f prime is going to equal derivative of that. Derivative 2 over x, that's 2 times x to the minus first. Its derivative is minus 2 times x to the minus second. So simplifying this, and I do think it's worth your while to simplify these things. This is 2 minus 2 over x squared. And I really think for things like this, you want to get a common denominator. So this is going to be 2x squared over x squared minus 2 over x squared, which is 2x squared minus 2 over x squared. Factoring out the 2 times x squared minus 1 over x squared. Factoring the top, 2 times x minus 1 times x plus 1 over x squared. Okay, so we have a few critical values here. The critical values are x equal to 1, x equal to negative 1. And yeah, I'm going to include 0 even though it's a pseudo-critical value. Right? 0 isn't a real critical value because, well, yes, it does make the derivative undefined, but it wasn't in the domain of the function to begin with. So it doesn't really count. So let's look at the first derivative test. So I do need to include 0 on my number line. And then you just test points on either side of it. So pick a number larger than 1, like 5, plug it in to the derivative. Positive, 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 great. Pick a number between 0 and 1, like a half. Negative, positive, positive. Negative 1/2. Negative, negative, positive. And that seems wrong. That seems real wrong. Let's be smarter than that, James. I said negative, negative. That was a lie. Negative 1/2 would give me negative, positive, positive, which would be negative overall. And then finally, negative 4, negative, negative, positive, gives you a positive overall. So it's increasing, decreasing, decreasing, increasing. So we have a relative maximum at negative 1. We have nothing at 0, not because it's negative, negative, but because the function isn't defined there. And we have a relative minimum at x equal to positive 1. Yeah. Let's go ahead and talk about, what's time of that? So it's always like, do I want to look at this one? Not really. But yeah, let's go ahead and talk about some second derivative stuff here too. So, yeah. So here's the deal about finding second derivative stuff, meaning concavity, points of inflection, and all that kind of jazz. You really, really want to not actually use the factored form of the first derivative to differentiate again. I would rather use this to differentiate again. But let me say a couple things about concavity, just some very, very basic things. So here is a very general picture of something that's concave up. This is concave up, like a cup. And a function that's concave up has, basically there's 3 ways of saying a function is concave up. You can say it's concave up. So I should say, right, if this is f of x, I'm really saying that the function itself, f of x, is concave up. But you can also say this in saying something about the derivative of the function. So if the function is concave up, the derivative is increasing. Let's think about this. So what we're saying is the slope of the tangent line is increasing. From, and again, when you talk about increasing or decreasing, you always mean from left to right. So from left to right, the slope of the tangent line starts off very negative. And then the slope of the tangent line becomes less negative. So it increased, right? If you went from negative 10 to negative 5, you got bigger. And then 0. Okay, we increased again, right? Negative to 0 is an increase. And then slope of the tangent line is slightly positive, so we increased. Slope of the tangent line is more positive, so we increased. So in this whole concave up kind of picture, the derivative is always increasing. Well, we know that if something, and so don't look at this for a second. If something is increasing, Like if a function is increasing, its derivative is positive. So if a function is increasing, its derivative, the second derivative, right? The derivative of the first derivative is the second derivative. So if something's concave up, there are three ways to say that. You can say it's concave up, you can say the derivative is increasing, or you can say the second derivative is positive. All three of these things mean the same thing. And then similarly, if the function is concave down, like a frown, you can say that the first derivative is decreasing, because from left to right, it starts off very positive and then becomes less positive, and then 0, and then negative, and then more negative. Or you can say, well, again, if a function is decreasing, its derivative is negative. Another way to think about concavity is, right, if it's concave up, it's opening upwards. If it's concave down, it's opening downwards. And sure, I can draw something here. If you had a function that kind of looked like this, for example, and you ask where is it concave up and where is it concave down? Well, it's clearly concave up somewhere around here, concave down somewhere around here, up somewhere around here. And the way to see where the concavity is changing is, well, if you view this like a road where you have the top view of the road. If you think about a car and you're driving along the road, like here's a little car. I'm not so great at drawing. So there's a car and it's driving along this road, right, but right from the top down. So like you're seeing the car drive on the map. As the car goes this way, it's making a left turn. Left turn, left turn, left turn. And then right about here, we stop turning left. So here we're turning left. And then here we start turning to the right. Until about maybe right there. Where again we start turning to the left. So when the car is turning left, the function is concave up. When the car is turning right, the function is concave down. That's another way to see it. So this is a really, I think, helpful interpretation if you're actually just looking at a graph and being asked, like, where is the inflection point? Well, it's where the car stops turning left and starts turning right, or stops turning right and starts turning left. It's a place where the direction of concavity changes. Yeah, I don't want to do this assumption. I thought I did, but I don't. Let me see if I can throw a quick example at you guys. Yeah. For anyone plus. Oh, cool. That's nice to have a Quizlet. So let's look at this one. So let's look at f of x equal to x to the fourth minus 4x cubed. Now I would like to know all the things about it. Increasing, decreasing, inflection points, relative extrema, all the jazz. So first of all, let's find f prime of x. It's 4x cubed minus 12x squared. I'm going to factor it to find the critical points. So factor out of 4x squared, you're left with an x minus 3. So my critical values are x equal to 0 and x equal to 3. You put them on the number line and see that if you put a number bigger than 3, like 4, positive, positive. Putting a number between 0 and 3, like 1, positive, negative. Putting a number less than 0, like negative 1, positive, negative. So your function is decreasing, decreasing, increasing, which means we have a relative minimum at x equal to 3. We do not have a relative minimum or maximum at x equal to 0. Decreasing, decreasing. I would also say that the intervals of increasing, decreasing are, it's decreasing on the interval from negative infinity to 3. Right? We include the 0 because the function is certainly defined there. It's increasing on the interval 3 to infinity. Okay. Let's look at the second derivative stuff. So the second derivative here, and again, even though I like the factored form to help me see things, I want to use the unfactored form to take the next derivative. So the second derivative is going to be 12x squared minus 24x. Set that equal to 0 to find the critical values for the second derivative. So I'm going to factor out a 12x. I'm left with an x minus 2. So my critical values for the second derivative are 0 and 2. So pick a number larger than 2, like 3, positive, positive. Pick 1, positive, negative. Pick -1, negative, negative. So this means that the function itself is concave up, concave down, concave up. So it's concave up on the interval from negative infinity to 0, union 2 to infinity. It's concave down on the interval from 0 to 2. And we'd say that we have inflection points wherever the, so I should say, you have an inflection point. Gosh, the actual definition of where an inflection point is can be a little bit complicated. It's essentially where the concavity changes and the function has to be defined there. So function is clearly defined everywhere. So we definitely have an inflection point at 0 and at 2. Inflection point at x equal to 0 and x equal to 2. Because at 0, the concavity changes from positive to negative, and at 2, the concavity changes from negative to positive. Something to be aware of, unlike with maxes and mins, where it matters if you're going positive to negative or negative to positive, it doesn't matter with inflection points. Inflection point is just where the concavity changes. It doesn't matter if it's changing from positive to negative or negative to positive. Okay, one last thing I want to say, because this is kind of important, but not really. You guys have probably either have heard or will hear about the second derivative test for relative extrema. So what that is you can take your critical values from the first derivative and plug them into the second derivative. So yeah, I'm doing it. So here's what I mean by this. You can say, okay, I'm going to plug in 3 to the second derivative. So f double prime of 3 is 12 times 3 minus 2. I don't really care what the value is, although it is 36. I just care that it's positive. Here's what that tells me. That critical value from the first derivative is where I either have a max, a min, or neither. But since the second derivative is positive, that means at 3, the function is concave up. So at 3, which is either a max, a min, or neither, the function is concave up. Well, that means it has to be a minimum. So we know that we have a relative minimum at x equal to 3 because f double prime of 3 is positive. That's the essential gist of the second derivative test. If you take your first derivative critical values and plug them into the second derivative, it can, but not always, tell you if you have a relative max or relative min. The issue there is we plug in 0, f double prime of 0 is equal to 0, which doesn't tell you anything. If the second derivative is equal to 0, you could have a max, you could have a min, or you could have neither. In this case, it's neither, right? We know that from the first derivative test, it was neither a max nor a min, but that's not always the case, right? If your function was g of x equal to x to the 4th, which definitely has a minimum at the origin, right? It looks kind of like this. Kind of like a parabola, but not really. The first derivative is 4x cubed. You definitely have a critical value at 0. The second derivative is 12x squared. Plugging in 0 into that still gives you 0. But here you have a minimum, whereas plugging it in there you got 0 for the second derivative and you didn't have a minimum. So the sum up here is that second derivative test is fine, but it doesn't always work. And why would you use a test that doesn't always work when you can use a test that for sure always works? So the first derivative test for relative extrema is always going to be our test of choice, unless someone specifically says, use the second derivative test because I want you to. the reason you, and sorry, I know I'm way over time here. I'll say one last thing and then I'll stop. The reason we care about second derivative test is because when we take 16C, there are functions of multiple variables that we want to find the maxes and mins of. And then the only real way to do that is to use a three-dimensional version of the second derivative test to see if we have a max or a min. So that's where we're going with the second derivative test. In 2 quarters, we're going to use it for some stuff. But for now is the time to talk about it because we're talking about concavity and second derivatives, but it's really not the test you want to be using currently to see if you have a relative max or a relative min, although you can.